Hello everyone. So in the previous lecture we studied about the basics of medical imaging. I also explained you about different types of images. I also told you about pre-trained models. Also the benchmark data sets over which these pre-trained models are trained. And I also introduced you a very important thing, that is convolution neural network, because these pre-trained models are based upon CNN. Okay, so how our flow goes in the study. We do have a data that we are calling as medical images, and these images will be in format of either JPG or PNG. They will be gray scale images because we do have X-ray, we do have MRI, we do have ultrasound images. Okay, and then we have to use this images as a data, and then we have to perform pre-processing of this data. That means we have to perform cleaning of this data. That's what the pre-processing means. And then I need to put up this into a model for training purpose, because I want the machine to understand what this data is about. Okay, fine. And then once my model got trained, I can evaluate my model, what results it's giving. I can perform prediction from my trained model. Okay, that's what I can do. Okay, so in regards to that, CNN, convolution neural network. That's what we were discussing. And in CNN, you are available with convolution layers and neural network. Okay, that's what you are having. Okay, and in this architecture, because we are going to build the architecture, the convolution layers are feature extraction technique. Okay, when we give image as an input here, this convolution layer is going to extract the features from the image. How it extract the feature, I have demonstrated you, I have shown you in my notes. Okay, where we were having the metrics of the image, and we are having this as a kernel matrix. So this kernel is going to operate over the image, and it will be result into another matrix that will be of less dimension than the original one, because you know the formula which we use here is given as 1 plus height of the image plus 2 into padding minus height of your which we calling it as filter or the kernel. Okay, so here you can put, then divided by the striding, that will be the resultant height, and this will be the resultant width of the image, that is like wi plus 2p minus wf divided by s. Okay, so you will get the resultant as hr and wr. We have already covered this thing in the previous lecture. Okay, so I have also shown you the code. Again, I am showing you the code. Let me share my entire screen and I will explain the maths which is involved here in performing the convolution. Kindly recheck the code. Okay, here it is. Fine. So in this particular code, yes, we perform the transformations. I explained that thing in the previous class. Okay, here it is. And in this particular code, we have implemented a convolution layer, single convolution. Okay. Now, when you want to perform deep learning, okay, so in deep learning, you are having some framework. This framework provides you support to perform the implementation, coding, all the mathematical calculation, and everything which you want to perform with the data. Okay, so this support, which I'm calling as a framework, they are TensorFlow and PyTorch. Okay, TensorFlow and PyTorch. We do have these two as major framework. There can be other frameworks also, but we do have these two frameworks which are mostly used. The TensorFlow framework is of Google, and PyTorch is a framework of Meta. Okay, and both are the famous ones. This has been more used nowadays, PyTorch. Okay, so if you see the code here, I have already installed TensorFlow, this library in my system. So from TensorFlow, from Keras, from models, I have imported sequential. Okay, so remember one thing. The architecture, the model which you make is a sequential model. Sequential. Okay, sequential. So you are having a layer, a layer, a layer that all are present in a sequence. Okay. So we do make a sequential model. All right, got it. And that's the reason we call it as neural network. Okay. So we are having the neurons over these layers. Okay, and they all are in a sequence. So the training will be from this left to right. That means the flow of the data. Okay, there will be a flow of data from left to right. Okay, and then once you get an output here, that will be compared with the original output, that will be the actual, this will be your model given, then errors will be calculated. Okay, errors will be calculated, and then there will be a back propagation. Back propagation means you need to adjust the parameters of these neurons, that means the weight and the bias. That's what you need to, what you have to just check. Okay, you have to perform the optimization, you have to adjust the weights. So that's what we call as a training. So this is feed forward network. Feed forward network, that means the data will be traveling from left to right. You will be getting an output, and then you will be calculating an error what your model produced. and then there will be adjustment in the parameters, that is called as a back propagation. You will come back to the original one again from the layer number 1, and again the feed forward will work. This is what happens in training. Okay, anyways, in the code, if you see, I am having a sequential model and I have taken one layer, that is convolution layer. You know what's the purpose of convolution, and this is how you are going to add a layer in a model. Convolution 2D 16, 16 are the number of filters. Yesterday only we have discussed. The size of these filters is 3 cross 3. Okay, so you will be having an image. The input image is of 28, 28, 1. Okay, so you will be having an image of resolution 28 cross 28. That means 28 rows, 28 columns. This is the your resolution, the shape of the image. One means this is a grayscale image. Okay, you already know what is a grayscale, and you are available with the filter, that is 3 cross 3. That will be a filter. You are available with 16 such filters. Okay, so just make 16 such filters. All right, fine. And your image will be convolved by all these filters, by all these 16 filters. That means you are having all the 16. This eye image will be given to all the filters, and these filters, as I said, it is 3 cross 3 matrix. What kind of entries are present in it? That is being randomly assigned. The task here of the filter is to detect the edge, is to detect the corners, is to detect the relevant features which are present in the image. That's what the filters do. Okay, fine. So initially there will be a random assignment of the filter values. Okay, so this is F1, this is F2, this is F3, and this is F16. This will produce an output, this will produce an output, this will produce an output, this is all will produce an output, and all will be stacked. All will be stacked, kept one above the other. This is what happens. Okay, so the result which you will be getting is now having a depth of 16, because there are 16 filters. So result which you are getting is now having a depth of 16. And the matrix which you got here, every matrix you have to calculate the shape of that particular matrix. That I'm thinking right now, I think that will be like 26 cross 26. Okay, you can put the values in the formula and you can get it. So you will be getting the result. Okay, this matrix will be 26, 26, 26, 26, 26, 26. All will be 26, 26 matrix, and there will be 16 such matrix. 16 such matrix there will be. Okay, check out the code. Okay, 26, 26, 16 such matrix you are having. Okay, so 26 is the width, height, and 16 is the depth, because we are having 16 such metrics. One is the number of image. See, you have only input one image. You have only input one image here. Okay, that is image resized. That's what you got from above. Only one image you have put. Okay, so your data comprises of only one image. So the result here is 1, 26, 26, 16. Okay, and if you are having many images, so the result will be according to the number of images. Okay, so it may be like if you are having 60,000 images, the result will be like this: 60,000, 26, 26, and 16. This might be the answer. Okay, that will be the batch size or the number of images. This is width, this is height, and this is the depth. Okay, so width, height, and depth. So as many as filters you do increase, You are increasing the depth. Remember, no one will explain you what exactly happened. I am telling you here what exactly happening in the convolution. So the point is pretty much clear. You are having a matrix, you are having a kernel, not a kernel, you are having many kernels, and you are getting a resultant matrix. Depends upon the number of kernels, you will be having as many as number of such matrix that will be stacked one above the other. They are having the same shape 26 26. Okay, and they are followed by the number of images which we are having in front. That is why if you will see the result which you got 1 comma 26 26 1, this is tensor is a high dimensional data. You can see it's not 1D, it's not 2D, it's not 3D, it is 4D. It is 4D. 1, 2, 3, 4. Four dimensional data. So it's high dimensional. So it's a tensor. Okay, that's what the name TensorFlow is, the library, is the framework which we are using to perform this task. It's high dimensional. Okay, for that deep learning has been used. All right, got it. Fine. So concept of depthness is the number of input images. No, sir. It's not the number of input images. The depthness stands for the number of filters which you have used. Okay. This is, sir, your number of images, and this is your number of filters. So this defines the depth. This is the depth. You have used 16 filters, so the depth has been increased by 16. This is the shape of the image, that is the width cross height, and this is the depth, and this is the number of images. Number of images. This is the overall dimension which I am telling. Either it is the number of images or either it is the batch size, in how many batches you are taking the images. So for example, in the given code which I did here, that's only the one image I am available with. Okay, only one image I am having. Okay, here you can see image resize, that is only one image of just x-ray. So the result you got it as 126 26 16. Okay, that is your features, that is your extracted features from the image. And if you tell me, sir, kindly show what the CNN extracted from the image, so this is the answer. You can print the feature. This is what result, all number, everything is numerics here. These are the numerical values which are extracted from the image by the CNN. And obviously, you will see all 16. Okay. So all 16 you will see. So there will be like okay, only one image. Then I am having 26 26 as the resolution, 26 26 as a resolution. Okay, and all will be like this, and 16 from 1 to 16 like this. Okay, so it will be like 4D. Okay, you can see these are the values, extracted values by the CNN. Okay, got it. Fine. This is how CNN works. I will be demonstrating the codes related to the pooling also, different types of pooling. I will demonstrate the code. Okay, meanwhile, as we have learned this concept related to the CNN, okay, and also you can display these all 16 that I have extracted the numerical values from the given image, how it looks like. You can convert these numbers again into images. That's what I did. You can see here. Features dot shape minus one. What it mean? It determines the number of filters in the features. There are 16 features. So minus one is the last one. 16. So pick up that one. Pick up 16. Then I'm going to make the subplot 4 cross 4. That means I will be representing the image 4 rows and 4 columns, because I know the number of filters I used is 16, so I can represent it in 4 into 4. I can do that. Size of the figure is 8 comma 8. Again, this is the width and height. This is the fixed size. Okay, and here I applied the loop for I in the number of filters minimum 0 to 16. It will loop will run, and IM show will show the images. It will show the images. Here I have mentioned every step which I have used. Okay, so I will be creating a grid of 4 cross 4, and then I am going to perform the reshape of this into one dimensional, making it easier to iterate over the subplot. That means you are having a subplot of 4 cross 4. However, there is a function called as Ravel. Ravel will convert this 4 cross 4 into 1 cross 16 for its analysis, but you will be seeing it in 4 cross 4 only. But Ravel will do it, will access it, will that is created as a grid 4 cross 4 is reshaped into 1D for easy interpretation. Okay, fine, and then I'm going to apply the loop according to that over it. Okay, and here I'm going to display the feature map, the extracted features which we did using the CNN, and then I'm going to display it. All will be displayed. So here it is. So CNN, this is what CNN extracted from your original image. I don't know whether you have seen previously or not, but this is what is been extracted from the image. This is okay. Corner, you can see corner is extracted somewhere. You can see intermediate also pixels extracted. Here it's complete darkness. Here it is something else. This is more bright. Okay, so this CNN with respect to different kernels, it is extracting the pixels from the image, and you are showing the grayscale. This is okay, much more highlighted, much more bright. Okay, here you can see the pixels, grayscale. This is how information is being extracted from the given data. This is how the CNN works. All right, got it. So though it is a very basic code, but it will work as uh, okay, very important for you to understand the working of CNN. Okay, fine. Now what I am having, let me talk about the code. Let me talk about the code. Brain tumor classification. Okay, let me talk about this thing. So I have done the code on the Kaggle. Okay, that's what I did. Fine. So here it is, brain tumor classification. This is my code. And before working on the code, I need to show you the data, because data is very much important. So brain tumor, okay, brain tumor, what it is. I hope you are able to see my screen, the coding screen, the Kaggle. Brain tumor, if you want to work upon the projects, I know you guys are been doing research or the projects, and you are aware of these things. Okay, for example, your problem statement is brain tumor classification. Okay, so in case of data science and machine learning, we should be knowing the first the basics. What is brain tumor? What, how many kinds of tumors are there? Okay, and if you are available with the data related to it, how can we classify? What kind of algorithms we can use for it? Okay, so in regards to that, I have also prepared one template for you. Okay, that's what I did. Brain tumor classification, I am having a data set. Okay, and let me show you the images first. This is what I am having. Brain tumor classification. Okay, this data set I am working. Okay, you can find it on the Kaggle. That's from there only. Now I am showing you. Okay, it is having two directories, train and the test. This is the train directory. In this train directory, I am having four further folders: Giloma, meningioma, no tumor, pituitary. No tumor, that means okay, these are the images of the brain MRI, which are not having any tumor. Rest these are having the tumor. Okay, and if you click on any of the folder, you can see the images that are present in JPEG. You can see the images. So we will be having the images of four categories. Okay, this is the image of one of the category which I have opened right now, that is glioma. Okay, you can look for meningioma also. Okay, this is meningioma. All right, and then you are having an image of no tumor. This is no tumor. Okay, in this MRI images, I don't have any kind of tumor. Okay, and then this is pituitary. You can click any of the image. This is pituitary. Now you are seeing, sir, all the images are looking like similar only, sir, black and white image. Okay, like a grayscale, all the images are looking similar, and you are telling that, sir, we will make a model that can classify all these four. How is this possible, sir? Everything is looking like grayscale, black and white, sir. If you see this image, if I give you this image, and if I ask you, kindly tell whether there is a cancer or not, tumor or not, will you tell me? Are you able to see this image, and can you tell me that there is a cancer or not, or tumor or not? Is it possible for you to tell? Well, this is pituitary. This is no tumor, malignant. Everything is like looking same. Any of the image if you can pick up. Okay, maybe some shades. From this you can identify, sir, this is looking like a tumor, sir. This is looking like a tumor. This particular region, this particular area. So how we can make a machine to learn and understand that this is a tumor? What we are going to do? So let's discuss about the data. I have shown you the images, and we are having the four different categories of the tumors here. So the data set is of MRI images of the brain tumor, which can be used for the classification and the segmentation task. The goal is to develop the model which can assist in early diagnosis, detection of the brain tumors. That's where we are expecting the machine learning or AI to help us. Okay, that's what we want. Okay, fine. All right. So the data set includes MRI scans, and we are having presence of different tumors, glioma, meningioma, pituitary, and no tumor. They are in JPG format. Okay, joint photographic expert group. That is the format of the images. All right, got it. So yes, then what does it mean that these four categories? Glioma. See, glioma is a type of brain tumor that starts in the supporting cells of the brain. It can grow quickly and spread to other parts of the brain, causing headaches, seizures, problems with the movement or the speech. Okay, so such kind of tumor, it get starts from supporting cells of the brain. We are having meningioma also. It is a tumor that grows from the meninx. See, these all are the technical terms which are used in medical. Maybe I don't know where these meninx are present. They are telling it's a protective layer around the brain and the spinal cord. So we can imagine. Okay, so these names were given according to the location of where they are present. So meningiomas usually grow slow. Often they are called as benign. So they are tumors, but they grow slow. However, glioma, this one, glioma, they grow fast. They quickly spread. So we need to take care of this glioma. Okay, so there are the treatments also mentioned: surgery, radiation, chemotherapy. Okay, here also surgery, radiation. Okay, fine. And then pituitary tumors also we are having, which are grown in the pituitary gland, a small gland that controls the hormones in the body. Okay, so there these are been built up. Okay, they can cause hormonal imbalance. Again, weight loss, weight change, vision problems, headaches. So treatment, again surgery, medication, radiation. All right, and the key points here are, because we want to use the AI to perform the early prediction, early detection. Okay, so gliomas, they are very dangerous and grow fast. Early detection is mandatory here. Meningiomas are usually slow, not cancerous. Okay, so we can track and we can perform the diagnosis, but still it may cause the problem. Pituitary tumors affect the hormone. Okay, and they can cause a variety of symptoms. There can be a variety of issues with the pituitary tumors. So doctor perform MRI, CT scan, lot of things they do. Okay, so in this data, I'm literally sorry for this thing. Okay, because you have to for this particular day we have to manage. Okay, I also don't like the sounds and this thing, but anyhow. Okay, so yeah, the data set consists of 18,279 images. Okay, and we are having four classes, four tumors. I have already shown you. We are having the four tumors, four classes. One is no tumor. One is no tumor. Okay, fine. So three tumors and one is no tumor. Okay, application, what we have to do is we have to build models. Okay, machine learning, deep learning models, and we have to perform the classification of the images. That's what we have to do. So, obviously, this comes under the medical research, enhancing and understanding the tumor characteristics through image analysis. That's what we have to do. Okay, so images of MRI, brain, four classes, three of the tumor, one is no tumor. Okay, total number of images available are 18,279, and we have to build a model and we have to train a model based upon that. So how you are going to proceed for this problem? Because I am having the many people who are doing their research, who are working on variety of projects, different projects. Okay, fine. So how you are going to approach for this particular problem? Okay, so let me tell you what I do. What is my approach? Let me tell you this thing. First of all, now again listen carefully. There may be disturbance that, but they will not distract me. Neither I think that they should distract you. Okay, fine. What is the step which we have to follow? Step number one. Step number one says that. Step number one says that we have to understand the data. Okay, we have to understand the data. Okay, and that's what I already told you, that these much images number we are having, four categories we are having, and grayscale images we are having. Okay, explain the data. What task you need to perform? What is the problem statement? You know, I need to perform the classification, it is mentioned to you. So you have defined your objectives for that. Okay, fine. Step number, the next step is I will be doing some exploratory data analysis. That is step number two. I will be performing some EDA. Okay. And to perform the EDA, the simplest method which I do follow is I will be taking the image path, where the image is located, image path, and what is the category of that particular image. For example, the image is located in my C drive, in Python, in brain tumor folder, and this is the image 1.jpg. This is the image. What is the category? Okay, sir, Benning. Benning, or I would say meningioma. Okay, then another image in my C drive, Python folder, brain tumor folder, 2.jpg. What is the image? Sir, no tumor, no tumor. This is the image. No tumor is the image. Okay, this is the category. So what I'm looking forward to do here is I want to create a data frame. That will be my first step, where I will be available with the image path and I will be available with the category of the image. That's what I will be doing. Okay, got it. This is my first step, first approach. Then I will count how many images of category. We are having four category now. So how many number of images are for this category? How many 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 images are there? Okay, it's been told to you. You are available with 18,000 plus images. But how many for this one? How many for this one? How many for this one? And how many for this one? Because there is an issue. There is an issue. If you are having the number of images for one is 10,000, this is 2,000, this is 1,000, and the rest is, for example, 5,000. In this particular case, if you train your model with imbalanced data, imbalanced, if the number of images are not equal for all, then your model will be biased. The model will be giving the prediction towards the category over which it is being trained more. We never train our model with unbalanced data. We have to balance our data. For that reason only, I am checking how many images are there in each and every category. That's what I will do. And then I will, for just to show, I will display five images from each folder. That's what I will do. From all the category, just display five images. Then I will perform. Okay, first I will identify the number of images. I will display the images. Then I will check, because from here I will get that if the data is unbalanced, then I will balance it. I will performing the data balancing. Okay, I will be doing some sampling technique by the help of which I can balance my data. And then after balancing, I will be doing some pre-processing over the images. Okay, so now let's see the code, what I did. Okay, now check the code. You have to be very much attentive here, and this is the code for brain tumor classification. I will share with everyone. Okay, so when you do the coding on the Kaggle, you know that okay, you have to add the data. Okay, and after adding the data, here the data has been added, brain tumor classification, the data is added. One more thing I did is, because I need to train my model, these are the heavy models, pre-trained models, so I will be using GPU here, graphics processing unit, that I will tell you ahead. But first let me help you in understanding the code. Okay, so once you create a notebook in the Kaggle, and once you add data in this particular notebook, and when you execute this code, all the data is been accessed. The entire data is accessed. So here you can see in Kaggle, that is the root directory. There is an one more directory input. Then there is a directory called as brain tumor classification, in which we are having one more directory. Then we are having a test directory. Then we are having a pituitary directory, and then I am having an image on this. So once you create a notebook, once you run this particular code, everything will be accessed in this way. The entire data will be accessed. Okay, you can see all train and the test images of all the four categories will be accessed. Okay, it will do from its own side. Okay, got it. Fine. So here my data is entirely completely accessed. Let me increase the size. Okay, fine. So you will be able to see the code clearly. Okay, fine. All right, so here it is. I have also added the code for your convenience, like explanation along with the code. Okay, so once your data is accessed, now the thing is you do one step. Kaggle input brain tumor classification, brain tumor 1, train. This is the base path where all the training category images are present. So do one thing. First, first make a base path. Okay, got it. And then what are the categories you are available with in this particular train folder? You can see in my train folder. This is my train folder. In my train folder, I am having gloma, meningioma, no tumor, and pituitary. I am having these. Okay, got it. So I am having these in my train folder, all four. Okay, so here I have mentioned all four. I prepared a list of them. I have prepared a list of them. All right, fine. So I have prepared a list of them. Here you can see. So this is my base path, and this is the categories. Okay, fine. Then after that, as I told, I need to make a data frame. Okay, so image path and labels. I made two empty list. Okay, two empty list I made. Image path and the labels. And then I applied a loop for category in categories. Okay, this is your categories. For category in categories, that's a loop. And then what I'm doing is I am going to I'm going to join the path, that is base path, this path, with the category. I'm going to join the base path with the category. That's what I need to do. Okay, so Kaggle input brain tumor classification, brain tumor train will be the next. Will come gloma. Okay, that will be one of the path. Then meningioma, that will be the path. Then no tumor, that will be the path. Then pituitary, that will be the path. Okay, so four path I am joining with the base path. Four different categories I am going to join with the base path. And then I am going to again apply a loop in this category. That means what you did, if you check here, this is what I followed. I am having a base path. I am having category, that is the four categories I am having. Okay, so base path and these four categories. Okay, these four categories I am having, and there are images in these categories. Okay, there are images in these categories. Fine. So I joined the base path with this category, with this category, with this category, with this category, and then now I am accessing the images which are present in these categories. Okay, I am accessing the images which are present in these categories by this. For image name in OS list directory, apply a loop and then join the image with the respective category. Okay, so here I am doing, I am present in category number one. I am adding all the images which are present in this category. Then I will do with this, then I will do with this, and then I will do with this. Okay, that's what I am going to do. Okay, fine. That's what I will be doing. All right. And then what's next I am going to do? After performing all this task, okay, after joining all the images into the respective category and the entire this particular base path, I will be creating a data frame. pd.data frame, pandas I'm using, and I'm going to make a data frame. This is image path and this is the label for it. Image path and the label. That means where the image is present and what is the label. Okay, what is the label? Okay, fine. That's what I did. So my data frame is created, and this is how it looks like. Df.head, that means I'm going to show the first 5 rows of my uh, data frame. You can see this is the image path and this is the label. Df.tail, that is the last 5 rows of my data. Okay, so this is the image path and this is the label for that. Okay, so I want to create this thing only. All these are just like coding skills. It's not matter a lot. Only the thing is you should be aware of what task you have to perform. What you need to do. You have to create a data frame. Okay, and this is how you have to do. The code I will be sharing, you have to apply the same code, same technique with the data which whatever available with you. Okay, so just create a data frame. Okay, like image path and the label. That's what you do. Just follow my code. Okay, so that's what I got here. Okay, this is the shape 22,848 is the data frame. That is the in training I'm having 22,000 images. There it was present like some numbers. Here I got 22,848 images and the two columns I am having. Okay, these are the columns. These are the column names. Okay, I am having these four as the unique category. Four categories I'm having, four classes, and these are the value counts for them. This is the counting. For no tumor, I'm having 6,380 number of images. For pituitary, I'm having 5,828 and so on. So value counts. Things get become easy for us. If you are available with the images in respective folders, currently you have been given a data, train and the test. You are available with four folders in it. You are available with four folders in it. Right now, I am not talking about the test data. I am not doing anything with the test. I took only the train data. I took this thing. Okay, and I am having a base path, and whatever be the categories which are present in this particular train folder, I joined it with the base path, and then I joined the images which are present in this particular categories. Okay, and then created a data frame that made me a convenient way to perform the further analysis. And now by just performing this basic, what is the shape, what is the column, what is the unique value, what is the number of value counts, everything becomes easy for me. Okay, this is how I approach. And from here you can see the number of images is not same in each and every folder. New tumor 6,000, pituitary 58, meaning 53, 52. There is some gap. Okay, there is some gap. Okay, there is difference in the number of images. Okay, fine. So we will see ahead what to be done with that. Meanwhile, I can draw counter plot and pie plot. Counter plot and pie plot. That means counter plot, just to whatever be the counting which we got now, I will be showing the bars for them. This is what the count plot means. And the pie plot will let you know the percentage. Okay. The percentage. Okay. This is class 1, this is class 2, this is class 3, this is class 4. How much is the percentage of images? Okay. So count plot, I'm going to show the counting of the number of images present in a respective category. So that's what I did. Okay, it's very simple. Just use sns.countplot. Give your data frame, give your label. Label is that, this is label. This is label. This is a column name. Okay, fine. So give a label. Okay, x equal to label. Okay, and that's it. Only this line is important. Rest is optional. You can give a title to your plot, you can give x label, you can give y label. This is important. Only one line. Okay, and here I have made the pie plot. And what you need to do in the pie plot, you have to take the counting. Okay, you take the counting of number of images. Okay, and then Here you can create a pie plot that will show the distribution in fractions, percentage. That's what it will do. Okay, got it. So these are not so many like hard and fast things. Just since we are working on a certain project, so we can include such kind of plots in our research papers or some our documentation, some reports that okay, we got this number of images. We are available with this kind of data. Okay, fine, got it. So here you can see. Okay, this is my con plot and this is my pie plot. So 23%, 23, 25, 27, not so much difference with the number of images. Okay, so we are having a quite balanced data, but still we will look ahead what to do. Okay, got it.
Uh,
Then, yeah, please say. If any doubt, please let me know. All right, fine. So now, as I told, after performing the show of the counting, that is count plot and the pie plot, I told you my approach is to display the images. At least the person should know na, okay, what you are having in your data, to kindly show the images. Five images, 10 images, whatever you want to do. You can three images, two images, it's up to you how much you want to show. Okay, so I want to show five images from each category. All right, so I did the code with respect to that. So for that, I took import CV2. CV2 is a computer vision library. Yesterday also I told you about this thing, and we have introduced this CV2 in our code, previous code here, CV2. Okay, you have to install all these libraries. Okay, don't think like, sir, you are working so smoothly. I have installed first all the dependencies and then I'm working. Okay, got it. Import CV2. Number of images which I want to show is 5 for each category. Okay, this is the figure size 15, 12. 15 is the width, 12 is the height. And this is the loop. I'm going to apply loop in each and every category. That's what I need to do. Apply loop in each and every category. Okay, and this is each and every category. Okay, apply loop in each and every category. Identify. We are having four categories. Just pick one by one. Or pick one by one. And number of images which I want to display, number of, this is number of images 5. So I will be going inside the category by the relevant path, and i will I will be accessing the location index position where the image is present. I will be reading that images, I will be converting that image into RGB, and I am going to show it. That's what I'm going to do. Fine, got it. So let me tell you one thing. What happened here in category image path? See, all the images are listed like this. All the images are listed like this. Okay, like 1.jpg, 2.jpg, 3.jpg, all are listed. Okay, so I will be picking up a path for a category, and I will be accessing each, means I will be accessing the image. I need to just display five image. So let's say this, okay, 3, 4 and 5. Okay, here is the location 0 comma 1 index position. Okay, zeroth row, first column. Zeroth row, okay, this is 00, this is 01, this is 02, this is 03, this is 04. So according to the index position, just pick up the image and then display it. That's present in the code, and you are also available with the explanation too. I have given the entire explanation here. No need to worry about anything. You can see df label equal to category, whatever be the category you are having. corresponding to the path. Dot ILOC means location. Okay, so colon number of image, that means I require 5 image only, because number of images I already mentioned 5. So go in each and every category and display 5 images from each and every category, and that's what I did. Here you can see, this is glioma, this is meningioma, this is no tumor image, this is pituitary. One thing which you can visualize from here is, sir, the size of the images are not same for all. So okay, you are sir, you are having images, you are having images in the folders. Okay, you are having 4 categories. Fine. Glioma, meningioma, no tumor, pituitary. You are having images in them. But sir, the size, the shape of the image is not same for all. You can see here. Sir, this is different size. This looks to be different, sir. I guess there is difference in the size. Anyways, I haven't done anything. Whatever present, I'm just displaying it. I'm not doing anything else. Just display whatever you got. So till here, we have used our coding skills to show what we are available with. Okay, that's what I did. Nothing, no hard and fast coding, no hard and fast applications I have applied. Just I want to show what is available with me. Okay, fine. That's what you can see here. Okay. All right, got it now. So the explanation is given here in my coding example. All right, fine. And then next, what I need to do is, I am here converting my labels. The labels are the 4 names. Okay, that is your categories. These are the labels. Okay, so I need to convert them into numerical value. Okay, again see the data set what you are having, what you are available with. Okay, you are available with this image path along with the labels. You are having 4 labels: glioma, meningioma, okay, and then no tumor, and then you are having the last one is pituitary. These are the words. Okay, these are the words. These are like string. If I need to perform the further analysis, let me convert them into the numerical value. So 0 1 2 3, I need to convert them into 0 1 2 3. That's what I want to perform. Okay, so for that particular reason, I have used here label encoder. So from here the pre-processing starts. So far I was just showing what kind of data I am available with. Okay, what I am available with. And now I am performing the pre-processing. I am going to convert the labels. I am going to label encode. Okay, so this is what I am going to do. Whatever be the labels you are having, create the encoding of them, a numerical encoding of them. That's what you can do. Create the numerical encoding of them. Fine, got it. So now it will be encoded into the 0 1 2 3 4 numerical formats. All right, got it. And then I'm going to make a data frame with only image path and category encoded. That's what I need to prepare. Only image path and the category encoded. That's what I need to do. I don't need this thing. Okay, the original labels, I don't need this thing. Okay, I just need category encoded and the image path. Only these two I require. Okay, got it. So the initial labels I'm not considering. I'm making a data frame with these 2 columns only. Fine. So let me summarize you what I did so far. Okay. What I did is I am available with the images in folders. That's what I am having. And I performed the, yes Sarthak, please say.
Sir, what does label encoder helps us with? Can you explain once again?
Label encoder will convert your labels into numerics. That's what label encoding do. Okay, so in general, if I would say, label encoding is used for categorical data which is in order, especially ordinal data. For example, if I would say, the rank of the generals in the army, something like that, or I would say the rank in an organization or institution, from peon, then clerk, then manager, then senior manager, then you will be having what, the head of the department, then chairman, something like that, principal, chairman. So when we are having an order, there we use label encoding. Okay, however, we don't have any such orders here, like pituitary will come first, then your no tumor will come after that. No, that is not an order. In general context, I am giving a numerical representation to these various categories. Okay. So new tumor, for example, it will become 0. Pituitary will become 1. Gloma will become 2. Meningioma will become 3. Like this. This is label encoding. And label encoding is represented like this. If you are having low, medium, high, so it will be like this: 0, 1, and 2.
Sir, it doesn't carry a hierarchy, right? It's
Uh-huh,
just a
hierarchy. Like this thing. Like this thing.
okay.
Levels, layers, stacking, not hierarchy, it's a stack, not hierarchy, stack.
Okay, sir.
Fine. So that's what I did. Okay. So the approach which I have followed is, I took the path of my data, I joined the categories to it, I joined the images to it. Okay, I shown the five images in each category. I have also displayed the count plot and the pie plot for you. Okay, that's what I did. Okay, and a part of pre-processing in which I converted these categories into some numerical representations. That's what I did. And the reason is, next I need to perform the sampling of my data. Okay, that's what I need to do. Sampling means, if we are having the less number of classes in any of the category, let's make it equal to the maximum. Okay, for that reason, I have used random oversampling. Okay, there are two things. Sampling means, what do you mean by sampling? Sampling is a way to collect the samples from the data. This is your data, and I'm going to collect the sample from it. This is called as a sampling. Okay, I am having four classes: one, two, three, four. If any of the class is having more number of data, any of the class is having less number of data, I need to increase the number of data in that particular class so that it can become equal to the first class. That's what I want. For that reason, I am using currently random oversampling means, increase the number of minority class equal to the majority class. That is called as oversampling. We are having undersampling also. We are having so many techniques of sampling. Okay, got it. Currently, I want to oversample. Oversampling means, what is the highest number of data in a particular class? Sir, 10,000. So equal, make equal to 10,000 for rest of the classes also. All should have 10,000. How? By duplicating. Okay, doesn't mean that it will create something new. No, no. If I am having A with 10 values, B with 5 values and I need to oversample B to make it equal to 10, I will be duplicating these 5 values. I can duplicate any, like, and I can be adding 5 more, that will become 10. So duplication. Okay, we have to duplicate and make the things equal so that there should not be scarcity of data in any of the class. That's what we have to do. Yes, any doubt, please let me know.
Sir, is this like augmentation?
Huh? Okay,
Uh,
you're talking about augmentation. No, this is.
no, whatever you're
Ha ha.
telling now, that
Ha
is
ha.
sampling. So
Ha
it
ha.
is like augmentation.
See, what it's mentioned here, you can see. uh, I am going to balance my data. Augmentation, I will do transformation and then I will add. Okay, you can say a part of like that only. For augmentation, I am specific. Okay, for augmentation and specific kind of transformation. Here I am just increasing the number of samples in no transformation, just duplicating them. In augmentation, I do perform like transforming data, rotating the data, translating the data, flipping the data, horizontal, vertical. That means I do changes in the data. I do different kind of changes in the data.
That means in different dimension,
Ha
right?
ha ha
In case of
ha ha
augmentation.
ha ha.
But sampling means in the same copy of data,
Same
right?
copy of the data. That's what I'm doing. Okay, just
Then if it is the same copy of data,
huh.
so then it will not create the problem.
Well, there is a problem when you are using imbalancing. There is not a problem when you are creating a same copy. Okay, there is not a problem because we will be randomly using the data, not in a particular order. If you create a copy also, it doesn't mean that you are using the same data in a particular order. For example, I did created a copy of 5, so it doesn't mean the order will be the same. Okay, maybe the fifth will come, then 4 will come, then 2 will come, then 1 will come, then 4 will come. It's not like 1 2 3 4. Okay, so here the model will be learning according to that. We will shuffle the data. Creating a copy will shuffle the data. Okay, got it. So these are the good two questions. Are you performing augmentation? Augmentation is a way to increase the number. So yes, we can include this part as a this part. Okay, you are augmenting. Augmenting, that means you are increasing the number of images. So yeah, okay, uh, augmentation can be said you are increasing the number. That's what we call in augmentation. But the increase in the number which we did here is simply by performing sampling, and the sampling we did here is creating the duplicates of the data that is internally been done, and shuffling will be done. Okay, we'll shuffle the data ahead. We'll use further in the pre-processing. So it can be, it's a part of augmentation. Okay, I'm not denying that thing. It's a part of augmentation, this sampling. However, we specifically do the augmentation with keeping something in our mind. Okay, and that thing is like I told, rotation, translation, flipping of your data, and there are many things which we do. Okay, fine. So yes, this thing comes under the augmentation. It's a part of augmentation. Okay, any other doubt? Please let me know. Yes, please. Yes, ma'am. Yes, Asmita, you got this thing.
I got, but still now actually I have some question. At the end
Uh-huh.
of the session, I will ask you. Otherwise, it will the wastage of time.
Okay. So, all right, fine. Yes, any other doubt?
Thank you, sir.
Yes, sir.
Yeah, yeah. Please say.
I just wanted to reconfirm if this data is being copied. So,
Hmm.
from which category will it take the data? Like from
Okay.
which
See,
of
ma'am,
those four
in
categories?
a respect from respective category only. For example, I need to make B equal to 10. So from here only it will replicate the numbers. From C, I need to increase the number of C to 10. So from C only it will create 10. Okay, C is already having 4, for example. B is already having 5, for example. So 5 more, or just similar to this 5, it will add more to make it 10. I am having
So
4
it will
here.
not have this overfitting problem later on.
Oh, no, no. What kind of overfitting? Like you will say overfitting? How? In overfitting, we are having good results during training, but we fail during testing. That's what happens in overfitting. Okay, so that's not the case of overfitting here. Okay, overfitting will happen
Okay.
if you do work on unbalanced data. There overfitting happens because your model become biased towards 10 and rest are just 4 and 5. So model will get least learned from them. Okay, I want to make a model equally learn from the data. That's what I want. What's the reason for performing the oversampling? I want a model to learn from A, from B, from C to D equally. So there should be equal number of data values present in them. That's what I want. Okay, doesn't matter that I have done some kind of sampling where I did perform the duplicates. Okay, there is a duplicates. So one question is this augmentation also? So I said yes. Augmentation is a technique to increase the number. Augmentation is what we do, increase the number of data. So here, yes, I am increasing by sampling, but the way of increasing is not any specific in nature. Okay, we do specific augmentations also so that my model can get the variations. Here we are not getting a variation. That's the difference between the augmentation and the kind of sampling which we are using. That's the difference. Okay, and variation can be like this: rotation, translation, like this variations. Okay, fine. So that's not the case of overfitting. All right, got it. So I did perform the sampling here. Okay, here is the part of code for performing the sampling. And after performing sampling, all things I mentioned here, what are the different kinds of sampling techniques, I did mention everything. And you can see after performing sampling, all the category becomes 6380. All of them become 6380. Initially, when you check the number of images, what you are available with, here you can see in counting. New tumor is 6380. I am not touching it. It is the highest number. But whatever be the less I am available with, I am making it equal to 6380. We need to balance our data. I can undersample also. Undersample means reduce the number of images. But that will be a loss for us. It's better to increase, not to decrease the data. Okay, so oversampling. And I make everything equal. This is my resampled data frame, new data frame. Previously was DF, now this is DF resampled. Okay, got it. Fine. Now, are you able to understand? Please let me know.
So far, yes.
Okay, good, ma'am. Okay, oversampling to
Yes,
create
sir.
data
Thank you.
redundancy. Okay, all right. Code works well when the train, poorly on the test. Yes, yes, Mr. Babu, you are correct. All right, fine. I know that there is some, meanwhile, some disturbance, but we need to manage somehow. What for this day only? That's a last thing for the crackers and all, and then that's okay. Okay, fine.
That's fine, sir.
All right. So if I if I can give the time according to that, so I expect you are the people from where I can get the inspiration. So any kind of situation, if you work, so okay, that's what I'm trying to do. I'm sorry for the inconvenience, something which we have faced, but if you guys are with me, then everything is possible. Okay, so I've created a data frame.
No problem, sir.
All right, so we have created a data frame, and after creating a data frame, we need to perform some modeling, but I'm not going to switch ahead with that directly. Okay, let's discuss VGG pre-trained model. Let's discuss about this thing, pre-trained model. So far, you have done that. What is the step I do approach? What are the steps I do follow to treat my data? Then obviously the next stages are some part of pre-processing, and then I'm going to feed it to the model. Okay, this will be a model which I'm going to use ahead. VGG16. VGG is Visual Geometric Group. That's a full form. It's an architecture. And that architecture is made up of what? This architecture is made up of, like, again, CNN, that is convolution, pooling, convolution, pooling, convolution, pooling, and the neural network. Okay, so what kind of architecture is this we want to study? Okay, VGG16 proved to be significant. See, this is not the first architecture which was given. There are some primary architectures also, basic architectures also. I yesterday told we are having an architecture with only 3 layer. We are having an architecture which is having 5 layer. We jumped to 11, then we jumped to 16, then we jumped to 19. Slowly, slowly, as the research goes. So VGG16 is one of the significant innovations, and it is a convolution neural network that was proposed by these people, okay, at the University of Oxford in the year 2013. And this architecture is used in a challenge for image classification, ImageNet. There was a challenge in 2014, and this architecture was used to perform the classification of different objects. So we were having an ImageNet. I already told you about a database, a benchmark data set. And now these people were called, come on, use our architecture, and we want to see whether you are able to classify or not. Okay, they did that. So computer vision, you know, it evolved from 1959. By 2021 and 2024, we are now at a stage of self-driving car. There are so many breakthroughs right now. In 1980, the scientists they introduced neocognitron, that is the foundation of CNN. 1998, Lenet 5 basic architecture, a CNN for recognizing handwritten digits. See, from here only the things got started. The architecture was built for handwritten digit classification. Okay, and then an ImageNet, a competition was launched in the year 12, 11, 12, like 13, 14. So in 2012, AlexNet was one of the architecture was given. GoogleNet was the architecture which came into 2014. 2015, ResNet architecture came. So year by year, so many architecture came. And the goal of these architectures was they were based upon the CNN, and the task was to classify the images. Okay, although VGG16 didn't won the competition, GoogleNet did. That was much more advanced architecture than VGG16. But still, VGG16 is having something. Okay, it's having something important which we want to use. Okay, proposed in 2013. Unlike AlexNet and ZFNet, it is having convolution layers filters, 3 cross 3, up to 7 cross 7. But as I already told, we are not going to use the higher number of filters. Okay, 3 cross 3, 5 cross 5, max. Okay, so 3 cross 3 are used because it reduces the weight parameters as compared to the large number of filters. Large number of filter will do the complexity, so less numbers are used. Okay, so for simplicity and elegance, we are using 3 cross 3 filter. Okay, then there are many variations in VGG like VGG11, VGG16, VGG19. There are different variations. And what is 11, 19, 16 means? Number of layers. VGG11 is having 11 layers, 16 is having 16 layers, 19 is having 19 layers. Okay, so we want to study about VGG16, its architecture. VGG16 take an image of resolution 224 cross 224 as an input. with 3 channel RGB. Remember these things. It will take an image of resolution this 3 channel. It takes colored image as an input. We are available with the grayscale image in medical. So definitely we need to convert grayscale into color RGB. But you also know that it will increase the complexity, but still the kind of information which is available to us, that will be further distributed into two more dimension. That's it. Still your image will look grayscale only, but channels increased. Okay, anyways, uh, then we are having, in this architecture we are having convolution stack. That means the number of convolutions. We are having blocks. Okay, convolution stack. So in the first stack of convolution, there are two convolution layer with 64 filters each, 3 cross 3 size. Okay, 3 cross 3 size. Striding 1 pixel, padding 1. Striding 1 means 1 pixel by 1 pixel it will move. Striding I already shown you yesterday. In second convolution stack, it is similar to the first, but we are having 128 filter. In third convolution stack, we are having 256 filter. In fourth and fifth convolution stacks, we are having 3 convolution layers with 512 filter. So it is increasing the number of filter. Okay, so what's it telling? It's telling that, okay, listen, you are having convolution stack or block. This is CB1, this is CB2, this is CB3, this is CB4, this is CB5. In case of first convolution block, you are having two convolution layer, filters 64. Next again two filters 128. Then filters 256, then 512, something like that they have mentioned. 512 and I guess 512. Now who gave these people idea that you have to keep this much number of filter? You have to keep this much number of convolution block. Who gave them the idea? This is all experimental. This is experimental. This is done by the researchers. These people do work over the data. No one told them. They are available with the data. They have made this architecture. They have tested that, okay, if we keep the layers like this, so we will get the results accordingly. Let me show you the architecture also. Okay, let me show you the architecture. All right, so where is my, okay, brain tumor, VGG? Here it is. See, this is your image whose size is 224243. It will pass through convolution layer, and this is how the size of your image goes on decreasing. Once it passed through a convolution, its size got decreased. So let me tell you what happened. Okay, so two convolution layer in the first block with 64 filter, 3 cross 3 is the size. Then in the second block, I am having again two convolution, 128 filter, 3 cross 3 is the size. Again in the third block, I am having 1, 2, 3 convolution with 256 filters. Okay. And then in the block number 4, again 3 convolution, 512 filters. Then block number 5, 3 convolution, 512. That's it. Till here, I am having all convolution. Till here, I am having this convolution. Okay, so they made blocks. Okay, this is a block, 2 convolution. This is a block, 2 convolution. This is a block, 3 convolution, 3 convolution. Okay, and then at the here also block number 5, 3 convolution. My image will go from here, then from here, then from here, then from here, then from here, and then whatever be the feature extracted, I will keep like this, and this will be given to the neural network for training. And since you are seeing that the number of filters are increased, also we are using pooling. You can see after 2 convolution pooling, that is dimensionality reduction. I am having code for that. I will show the demonstration of this code also. Very, very basic. Then again, after 2 convolution, feature extraction pooling. So, sir, you told convolution pooling, convolution pooling. No, it is not mandatory. You can use 2 convolution, then pooling. You can use 3 convolution, then pooling. Yesterday, I got a question, sir, how we can make an architecture, how we can get the novelty, sir. Tough scene, sir. You can, that's what I'm teaching you, that this is the reference architecture. What they have used. Can you perform something? Can you do C, 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 and then pooling? What kind of results you are getting? Or either can you do CP, CCP, something like that? Can you organize the layer, something like that? Any chance? What does this C do? It extract the feature. Pooling, reduce the dimension. I want to reduce the irrelevancy in the data. That is how they have organized. Okay, this is your VGG16. How many convolution layers I am having? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 convolution I am having. And this. Okay, 13 convolution I am having in VGG16. And then anything else which you want to do? No, 13 convolution. And then I am having your, okay, 13 convolution and 3 fully connected layer. 3 fully connected means dense, dense, and dense. These 3. So 13 convolution plus 3 fully connected. Total 13 plus 3 equal to 16. This is what I mean. That is why it's called as VGG16. This is called as VGG16. And there is one more architecture, VGG19. They will add 3 more convolution. That's not much difference between VGG16 and VGG19. In VGG19, 3 more convolution will be added and followed by this only. That is VGG19. Okay, got it. That will be VGG. Here we are dealing with the VGG16. And here is a summary of the model. This is first convolution, this is second convolution, then pooling. Okay, after pooling, this will be the resultant matrix, resultant tensor which you will get. Then again, you are going to give this data to the convolution. This is the resultant. Every time you can see there is a reduction in the shape of the image. From 224, 224, it reduced to 112, 112. Then to 56, 56, 56, 56, all it's got reduced. Then 28, 28, it got reduced. Then at the last, it is now here 14, 14, 14, 14, and then 7, 7. This is the minimum shape. From 224, the image is reduced to 7, 7. So much reduction in the image. Yes, please say. Yes, Asmita.
Sir, I already asked, though maybe it is a silly question, but I need to ask you, that is, it is showing a none. What is the meaning of that one? That is none.
That is a batch size actually, Smita. Okay, I'm showing
So
a
batch
none. That
size-
is a batch size. Okay,
Okay.
batch. This is batch, none. Output shape, batch. Okay, and architecture will if you put the data over the training, architecture will define it. Initially, when you show the architecture, like you do a model dot summary, so it will show you like this. This is batch size, none, and you rest you very well know, width, height, and the channel depth. Okay, and I will also let you know how you got these values. 1792 parameter, number of parameter. I will also explain how you got this number 1792. So none is a batch, and I already told you, this thing, number of images, or if they are present in a batches, so what will be the number of batches for the images. You do also create the batch of images, no? So that's that number. Initially, I don't have anything. Once you put an image inside this thing, then it will show you the number. Currently, when you build an architecture, it don't show anything. That's why they have mentioned none. Okay, I hope this makes sense.
Batch means that is number of images I have. Whatever.
Yes, number of images. Okay. For example, as I told, if you are having 60,000 images, so that will show 60,000. But if you are dividing these 60,000 images into batches, so you have to define the size of the batch. What is the size? For example, 100 images in each batch. So how many batches will be created? 600 batches will be created for 60,000. So that will show the batch size 600. If you are dividing the image into batches, if you are not dividing the images into batches, then it will show 60,000. Got it? So we in general give the
Batch
data in a
means
batch.
it is the category, sir.
No. You train your data, that image data, into batch. No, you create a batch. Okay, batch. That's what I told. No, six. If you are having 60,000 images, you give data in batch. That means let me make a batch of 600 images. So in order to train 60,000, I will be making 600 batches. So this is first batch, this is second batch, this is third batch. That's what I'm doing. And dividing the data and keeping them in a batch. You got this thing or not? And keeping the data in batch. You are having the
Yes, sir.
batch size. You do have the batch size.
Yes.
Okay, so batch
I,
size, okay, for example, 32, 64, so 128, 256. That's what we give, batch size.
got it, sir. I got it.
Okay, so
Thank
that's
you,
what
sir.
it is. Okay, so this is the architecture of VGG. Okay, and that's it. That's what I need to explain in VGG. Nothing else. Rest things you can study. Okay, not hard and fast. Okay, and now let me tell you one more thing. Stay with me, okay? Unless and until I am here, then you are here. Okay, don't leave me. If you leave me, then I will feel very bad. Okay, thank you, Mr. Babu. I need that kind of support only. Thank you, madam. Okay, I will not take more than 5 minutes. Just be there with me. Like now, this is VGG 60. Now you understood, sir. There is some architecture. Yes, Mr. Abhijit. He will stay. That's what I think he is saying. So, क्या हुआ? What happened? In VGG 16, I told we are having 13 convolution and 3 fully connected. That means the dense layers. So convolution and the dense. That's what I am having. Total 16. Okay, and the arrangement of convolution is a smartness. The number of filters taken in the convolution is a smartness. You have to learn from this. Okay, and it's all experimental. Okay, that's what I told. Now, sir, can you show the basic code again for the convolution, this one? Okay, here it is. Here also, the question which is asked by Smita, sir, none is there, sir. Initially, when I build the architecture, I haven't given the image, how many number of images. Obviously, it will show none. But see here. Smita, here none is not present. No? Here what is present? 1. I was
It's
having
total number of images.
number of image. I am having 1.
Yes.
So now it show 1.
That question actually I have asked in the chat box.
Okay, chat box. You are chat
हाँ,
box. Okay, I think I
that
skipped
is
that.
none and one. Why it is
Okay.
showing initially it is none
Initially it's none,
and
but
in
when you give
output
the
layer
data, it's
and
one.
after that it is one.
Okay, fine. Now one more thing I want to say. Sir, what is this 160, sir? Okay, now listen. Look at this. Convolution 16. Okay, just look at that. Convolution 16, that means you are having 16 filter of 3 cross 3 size. Okay, so you will be having a matrix of this 3 cross 3. So total you are having 9 elements in this matrix. Okay, you are having 9 elements in the matrix. You are having 16 such matrix. So how many total elements you are having? 16 into 9? I think it is 144. Got it. 16 into 9, 144. I already told you that the numbers which are present in the matrix, they are parameters. During backpropagation, during training, the adjustment of these parameters only happen. I need to get the exact number by the help of which I can extract. That is what we are extracting from the image. That's a number game. So 3 cross 3 means 9. Total 16 filters. So 9 into 16, 144. One more thing. We do add bias also. Okay, we do add bias also, additional term as a parameter. So since we are having 16 filters, so I will be adding 16 bias to each and every filter. Total is 160. See, I don't know whether someone told you or not. This is the number of parameter, 160. Okay, so number of filters multiply what is the size of the filter shape, 3 cross 3. Okay, so 3 cross 3, 16 filters are there, 144, add 16 bias, additional parameter. That will be the number of parameters which will be trained. Got it? Fine. Yeah. Anything you want to say or ask, please go ahead. Please go ahead. And yeah, I have explained VGG16. I have explained this code also. My target is to complete the rest of the code for the brain tumor. And I will be using VGG16. I will also incorporate other layers to understand, so that we will be doing ahead. Let me, okay, please stay with me. I need to show the code again. Now, any doubt, please? Asmita, you were saying that you are having some issue, some doubt you want to ask.
Right now, can I ask
हाँ हाँ
as
बोलो बोलो बिल्कुल बिल्कुल पूछो पूछो ask.
thing is that sir
Let me
regarding
okay.